Hello, and thank you for logging on for my presentation, and thank you to the Wood and Fire Safety organizers for setting up the virtual conference. I am Laura Hasburgh, and today I'm going to present my findings on the chemical changes caused by pyrolysis in wood. With the development of mass timber products, wood is expanding into new building markets, including high-rise structures and large commercial buildings. However, the combustibility of wood still limits its use since thermal degradation, or pyrolysis, negatively affects its properties as wood is converted into char. Structural models assume wood is converted into char at a temperature of 300 degrees Celsius, resulting in a model with an infinitely thin pyrolysis front. The velocity of that front is known as the char rate, and char rates are used to calculate the residual load-carrying capacity of wood building products. Pyrolysis models often characterize the fire behavior into two phases: a solid phase problem, which includes the composition and generation rate of pyrolysates, and a gas phase problem with oxidation of those pyrolysates. While both structural and pyrolysis models are beneficial, neither consider the chemical interactions and changes that occur within the wood, and further investigation in this area is needed before more robust models can be developed. To evaluate the pyrolysis-induced chemical changes within wood, I utilized X-ray photoelectron spectroscopy, or XPS. From XPS, I obtained both low and high-resolution spectra to identify the elements and the chemical environments present. The high-resolution C1s spectra was used to obtain specific bond information on my specimen by fitting 6 sub-peaks. The binding energies and polymeric source for each subpeak are generally agreed upon in the literature for wood. For instance, the CO bond at 286.1 electron volts is attributed to the holocellulose, and the carbon double bond at 284.6 electron volts is from the aromatic rings in lignin. To develop a charged specimen with a known thermal gradient, a 20 millimeter thick Douglas fir specimen was instrumented with 6 vertically distributed thermocouples, and the radial longitudinal surface of the wood was then exposed to an incident heat flux of 50 kilowatts per meter squared within a cone calorimeter. The exposure was stopped when the unexposed surface reached 100 degrees Celsius, and using fire dynamic simulator, the temperatures between thermocouples were calculated. The charred Douglas fir was then cut into 4 millimeter sections, and a single late wood growth ring was chosen to conduct XPS on. Prior to conducting XPS, the section was soaked in acetone for 48 hours to remove extractives and then oven dried. Here on the left are carbon atom results from the uncharred edge of the late wood specimen, while the right is from the charred portion of the specimen. From these images, we can see that the CO bond is more prevalent in the uncharred wood, while the CC bond dominates the C1s spectra in the char. To evaluate the chemical changes through the pyrolysis zone, the peak ratios were calculated by comparing the area under each subpeak to the total C1s peak area. The peak ratios calculated from the C1s spectra are shown here on the left as a function of temperature. The lines have been provided to point out the trends in the chemical changes. From this plot, we can see that the CO peak ratio slightly decreases between 100 and 225 C. This decrease is potentially due to the cleaving of hemicellulose polymers and is spatially indicated by the box on the right. The CO peak ratio decreases again for temperatures above 300 C and is likely due to the thermal degradation of the cellulose. Additionally, the carbon double bond peak ratio did not increase until temperatures above 350 C, indicating that the aromatic rings from the lignin are not changing at these temperatures. Visually, the major chemical changes in the Douglas fir occur above 300 C, which is when the discoloration in the wood begins, but not yet in the brittle char layer of my specimen. The chemical changes obtained showed that the chemical bonds are changing even at temperatures below 200 C. These findings provide a deeper understanding of the thermal degradation of the polymers in bulk wood, and further investigations will compare these results to mass loss and mechanical changes within these same temperature ranges. I would like to acknowledge the participation of my colleagues, Drs. Stone, Zelinka, and Plaza. I would also like to acknowledge the use of the facilities and instrumentation supported by NSF through the University of Wisconsin Materials Research, Science, and Engineering Center. Thank you very much for your attention.